as much as possible. So without any due delay, I will just move the floor to Dr. Osama to start his presentation. Thank you all for attending.
Thank you, Dr. Ahmed. Thank you very much. Inshallah, today we will I'm going to present the research that I have done in the ITT 2022, enhancing deep training of image landmarking with image capture. I just want to make sure that you can see my presentation and you can see the pointer. Is okay?
Yes, possible.
Just confirm. Okay. So our agenda today, we will divide our work into two parts. The first part, I'm going to introduce the background concepts of the convolutional neural network, which is the main network that I'm going to build my research on. So first of all, I'm going to introduce it and introduce the basic concepts of it. What are the CNN layers, the types of CNN layers? We will see convolution layers, pooling layers, fully connected layers. We'll explain all of them. Also, I'm going to move to the second part, which is using the CNN in landmark classification, which is my main research. I'm going to present the research, the methodology, and I'm going to present the results and discussion. Actually, I'm sorry for the people are coming into the seminar, so I have to admit the okay. So what is the convolutional neural network? Actually, the convolutional neural network doesn't come in a sudden. It comes from a long research. For example, they started with perceptron. The perceptron is the basic element of any neural network that currently we are seeing in our research, in the field of neural network. The perceptron is very simple function that accepts 3 parameters. For example, it can accept more, and an output that relates these parameters with a function. The function is inside this circle. This is very simple function, which is a threshold function or a step function that accepts for specific threshold and reject for the same threshold. So basically, the perceptron is a function that takes 3 parameters or more and make an output according to the parameters. So it was back in 1950. And then we have many perceptrons connected together. So the concept of perceptron is expanded, and we have also another concept, which is the layers. So we have here how many layers? We have 1, 2, 3, 4 layers. And so sorry, we have a waiting. Dr. Ahmed, can you help me in admitting the waiting?
Yes, don't worry about that.
Okay. So the artificial neural network is a concept that came originally from the perceptron, and expanding the perceptron concept with new concept, which is layers. Then we have the deep neural network. The deep neural network has 100 and even thousands of nodes. This we call it nodes, and we have also sorry, we have also many layers. This deep neural network in the picture is a very common neural network that takes an image, a small image, and output if this image is handwritten numbers. The image has handwritten numbers, so it can decide if this image is 0 or 1 or 2 or 3. The number is 0 or 1 or 2 or 3 until 9. So if we, for example, if we input an image to this deep neural network, it can decide exactly which is this number, which is the number is written on the image. It can say this image is 2 or 3 or 4, whatever. So as you see, it is very intensive. And before that time, we had that concept of deep neural network, but actually because of the processing power, we don't have enough processing power to handle all of this processing, because it contains many or hundreds of nodes interconnected together, and it was very hard to process the forward and backward propagation, and because it needs high power processing. But currently we have parallel processing, parallel programming, and all of these technologies help in making deep neural network succeed. So we'll talk about the convolutional neural network. We will talk about the three main layers of convolutional neural network. We'll talk about the convolution layer, the pooling layer, and the fully connected layer. So first of all, we need to understand the CNN structure. If we look at this, the image to the right-hand side, we can say we have the CNN here, and we have an input image, and the input image is passed to the CNN, and the CNN output class scores. And according to this image, we can decide if this image, for example, is a dog or a cat. So the left-hand side, you can see this is an example of the CNN. It inputs a collection of images, and then accordingly decide if this image is a cat or a dog, or yeah, if we have two classes, so we can say if it can decide if this is a cat or a dog. Actually, the CNN works in two phases. The first phase is training. So we have to train the CNN on hundreds and thousands of cats and dogs, of images of cats and dogs. And then after training, we decide that we have a CNN module, and this module can be used afterwards in the classification process. So actually, the training happens in two phases. The implementation of CNN structure happens in two phases. The first one is to train the CNN, and the second one is to use it to classify. Okay, and then we have here the returning back. We have the CNN here. You can see this is the CNN, and if we look inside this CNN, we can see this structure. It contains a collection of layers, different layers. So we have an input image, and then the input image is passed by many layers until we get the class scores. So the CNN itself is comprised of number of layers. The layers extract features from the input images and reduce the dimensionality of the input image, and eventually produce classes. Actually, it reduces the dimensionality and
بس تشوفي حمدة يوم خذت المادة تعرفين شو؟
Okay, so we can see that we have many types of layers here. We have the convolution pooling layers, and we have the fully connected layers, and also we will add more layers after that. I will explain more layers that are important in enhancing the structure of CNN. So this is an example of CNN architecture. If you look at this architecture, is a common architecture. We call it VGG16. It is used for classifying 1,000 types of images. For example, it can say this is a tree, this is a car, this is a beach, or many labels. We can use this convolutional neural network to classify 1,000 labels. Actually, the structure is selected according to the application. This structure and the number of layers and the size of these layers is selected according to the application. We will go over each of these layers, and we will explain in detail. The first layer is convolution layer. The first layer in this network that processes the input image directly is the convolutional layer. The convolutional layer takes an input image and suggest it takes the image and filter this image in different, we can say in different filter, using different filters. So the filters extracts the features of the image. For example, if we have a high pass filter, the high pass filter extracts the edges of the object. The resulting features, we call it feature map. We call it feature map. An example here makes life easy. For example, if we have input layer, we have this image. We have also 4 filters: the first filter, the second, the third, and fourth. The first filter is taken an image, an input image, and output the feature map. The filter is simple. We have high value to the left and low value to the right, and you can see it extracts the vertical lines. Also, this one is extracting the vertical lines, but the direction of intensity is coming from right to left, and here the intensity coming from left to right. So they are both extracting the vertical line, the vertical lines or edges, but in different directions of intensity. Here also, this filter 3 and filter 4, it extracts the horizontal edges, but also in different direction of intensity. So the output, this is the output of the convolution layer, is a feature map, is like having different sublayers. We call these are sublayers of the convolution layers, because we extract the features of the input layer. The feature means, for example, edges, the objects, the background. These are the features. Each one of these feature maps representing a specific feature. Here, the idea of convolution layer. If you see, we have 1 convolution layer, 2 convolution layer, the second and the third convolution layer. But we have zoomed in this convolution layer to see what is inside it. We can see inside this convolution layer we have a sublayers, and these sublayers are the output of the filters. We call it feature maps. So we have here each filter in the previous slide. Each filter is extracting a specific feature map, and this feature map we call it sublayer. So this is the input. We have the first convolution layer, the second convolution layer, and the third convolution layer. But actually, not every convolution layer has the same filters. We can have different filters in each convolution layer. Okay, so this is the main concept here, that we have features, we have feature maps inside the convolution layer, and also we can have different filters in each convolution layer. They are not the same. I mean, how the inference work inside the convolution layers. The features that CNN detects are random in the first epochs. We can give the network random weights and biases at the beginning, and then the CNN start to detect the features. At the beginning, the feature will be random, and then it will be more focused during more and more training in the upcoming epochs. Another type of layers. So the first layer was the convolution layer. This is the second type of layers. We call it pooling layer. Actually, pooling layer is simple. It is here. We can see an example directly. We can see here we have the input image, and this is the output image. If we want to apply the pooling, we have the most common pooling here is max pooling. Max pooling is simple. If you look at this square, we have the maximum number is 6, so it outputs 6. Here we have the highest number is 8, so it outputs 8. Here we have the maximum number of 3, so it outputs 3. The maximum number here is 4, so we output 4. So this is the input image and the output image. As you see, we have reduced the dimension of the image. We have reduced the dimension of the image, but actually we concentrate more on the strong features. The max pooling concentrate on the most important feature, because we are taking the most important parts in the image, because this is the max. Max means, for example, if we have edges, we know that the max value will focus more on the edges. So this is an example. To the right hand side, you can see we have an input cat, and the output image is the same but reduced in the image. The third one, okay, so I'm returning back. We have the convolution filters, or the convolution layers. This is the first. The second type is pooling layer, and the third one is fully connected layer. Actually, the fully connected layer, we can find it at the end. It is like a vector. And the fully connected layer job is to connect the input. Sorry, I just want to minimize. So the fully connected layer is to connect the input it sees to a desired output, specific output. So here we have the input and we have the desired output, especially in the training process. So it converts a matrix of image features into a feature vectors whose dimension is 1 multiplied by C, in which C is the number of classes. So the output here, for example, here we can say that we have 1 multiplied by 1000. This means we have 1000 class labels. So this convolution layer can classify 1000 labels. Another function is softmax. Softmax is important to produce the class labels here, but they produce the class labels in probability distribution. So it can, for example, say which class is more probable than the other. For example, here we have the 1000 labels can be produced using softmax as probability distribution. So this is the main idea, or the main use of the softmax layer, is to produce the output or the class label as class scores. So we know the label with the highest probability is the class that we need. It's the correct class. When we use only 3 types of layers that we mentioned before, the convolution layer, the pooling layer, and the fully connected layer, only these layers is not sufficient for making good CNN. Why? Because we face the problem of overfitting. So what is the problem of overfitting? Actually, the overfitting happens in the training of the convolutional neural network. It means, like, if we train the convolution, or we train the network on, for example, thousands of cats and dogs. For example, say we train the convolution layer on 100,000 of images for dogs and cats. The overfitting means it can classify only these dogs and cats that it trains on. It cannot classify new samples. So it knows exactly what it learns. It cannot generalize. It cannot understand other features. As we know that we are in life, in our daily life, we can see cats in different shapes. We can see cats in different colors, in different even environment, in the snow, in the house, inside the bed. We can see many shapes for the same cat. If the CNN cannot generalize and understand the overall features of the cat image or the dog image, we can say that it falls in overfitting. So the overfitting means it knows exactly what it trains on. It cannot know anything else. It cannot know, it cannot decide or classify new images, new samples. That's overfitting. But how to avoid overfitting? We can add more types of layers. We have two types of layers. The first one is dropout layer, and also we will talk about the momentum. So the dropout layer is a layer used, added to avoid overfitting. We can, here we have, this is the dropout layer, is similar to training your muscles. If you want to make your muscle stronger, so you can, for example, if you train on your right hand arm only, so your right hand arm will be strong, but your left hand or left arm will not be strong because you train on one arm. So the best way is to train, for example, on Monday for the right hand side, for the right arm on all these sports, and then next day you train your left hand or left arm. So this way you can distribute weights on all of your arms, not concentrate on one arm and leave the other. So the same concept here applies on the neural network. So as you see here, we have epoch 1, epoch 2, epoch 3, and in epoch 4, we disabled these two nodes. So we distribute all the work on other nodes. This means we pay attention to the other nodes and neglect these two nodes. And also in the other epoch, we can remove this one and that one. In the other epoch, in the next epoch, we randomly, we can disable any two nodes. The probability of disabling is 0.2. This means we can just remove few nodes from the neural network during the training. So the dropout mainly used to not making the neural network focus on specific patterns. It needs to generalize. That's why we need to put the dropout layer here. The momentum is another technique. Actually, is not a layer, is a technique used to avoid falling in the local minima. If you look at the graph here, we have local minima and global minimum. We want to reach to the global minimum and avoid the falling into the local minimum. So if this guy is the performance of our system, so the training, in the training process, we have the gradient descent algorithm. It makes the system coming down and down and down until it reaches this point. But actually, eventually, it can fall in this point and say this is the highest performance of my system. But actually, it is not true, because we have another point which is the best point here. How to avoid sticking to the local minimum? We use the momentum. The momentum is just having a specific direction of taking the direction, and we can say multiply this direction and make it bigger while moving down. So the training can pass this point and jump over one edge, and especially if this edge is small. So it can jump over this edge and come into this global minimum and succeed to avoid sticking into the local minimum. So this is a technique used for avoiding local minimum, and it also enhances the performance of the CNN. Now we come to the next part, which is our research, landmarking with image capture. We introduced the CNN, and now we move to explain our research. So my idea is to use Google, similar to Google Capture. If you see, we have here labeling happens for the statue. So for example, if Google decided to select these two, and if the user selects these two only, it will be succeed to login. I can say I can add more images for the same class, and then the user can select them directly and add them to the dataset. So for example, these two images are selected. If the user selected them, it can pass. but also I can add more images of statues. So the user also will select them. It doesn't know which one or which two or which three he should or she should select. So it will add actually, or eventually it will add more samples to our dataset. So the main idea of my proposal is to have a CNN network, and the CNN network has input dataset, but actually I'm going to enhance this input dataset by adding more classified images from captcha technique, using captcha technique or captcha algorithm. So the captcha algorithm will produce more accurate classification, or you can say manually classified images to the input dataset, and then we can train our CNN on these new dataset. This is the proposed CNN architecture. If you see, we have an input landmark, and we have 4 convolution layers, followed by 3 fully connected layers, and the convolution neural network or the neural network can classify 50 classes. So we have 50 landmark types. The CNN can classify all of them. So here the dataset samples we can see we have these types of landmarks. We have Burj Khalifa here, we have the Sphinx in Egypt, and other types of landmarks around the world. The dataset contains hundreds and thousands of these types of landmarks. And this is the performance of my system. The performance here at the top for the system without correctly classified samples. We can say this is the training. The training is good, but after validation, we see the system is not performing very well. But here to the down, we can see that the performance of our training and the classification or the validation are similar. This means the performance is higher because the system here can generalize more than that. We can see this in this image that during the training, the system is talking about something, and during the validation is talking about something else. This means they are not correct. The system is not correct because it cannot generalize and cannot understand the pattern inside the landmarks. Actually, the landmark problem is very tough because the performance with the accuracy that we get in the research is about 44%, and using this captcha, I get 70% accuracy. Actually, the 70% is very high because it is well known in research that landmarking is very tough in classification. And here we have some images correctly classified. We have here samples of the image to the top and samples of the class labels. So for example, here, this is a part of the Eiffel Tower, and it is correctly classified. This is part, or this is the image of the Golden Gate Bridge, and also is correctly classified, and so forth. We have 4 types of, we have 4 images here as a sample. We can see that our system is correctly classifying the landmarks. And thank you very much for attending this seminar today, and I'm waiting for your feedback if you have any questions. And I'm turning it to Dr. Ahmed. Dr. Ahmed, are you with us?
Yes, yes.
Okay.
Thank you, Dr. Osama, for this presentation. Let me just repeat what we have highlighted at the beginning. The main purpose of this seminar is to try to find a co-researcher to extend existing work or to reach a perfection for an existing work. So this is the idea proposed by Dr. Osama. If you have any question, please go ahead and ask Dr. Osama. And alternatively, we are going to send an email about this presentation, and we will attach the presentation as well, and Dr. Osama email. So if you would like to have a one-to-one on, that is also a valid option.
Okay.
So if we have no question, I think we have reached to the end of today's seminar.
Yeah, okay, absolutely. And I think it's a good idea, Dr. Ahmed, to have this kind of seminars to exchange information between us and to cooperate, to find a way to cooperate between each other. Because,
Exactly.
you know, not all of us knows the same thing. Everybody has his own specialization and his own techniques that he is strong in. So we can cooperate, so
Exactly.
we can benefit from each other.
Indeed, Dr. Osama. This is actually the merit of this seminar, that we can complement each other. So if you require a certain skill that I have, I can help you and put my skills in your research and reach to a good research output. Thank you, Dr. Osama.
Yes, okay, thank you very much. So I think we can end this session. Okay.
Yes. So if we have no further question, I wish you to enjoy the rest of the weekend, and we hope that we can meet again next Friday.
Inshallah. Okay. Thank you.